Thank you very much. I hope you can hear me. So that makes it very difficult with this kind of introduction. The task is difficult enough. So core ideas in AI in a short time. So I don't know the background of the audience. I'm pretty sure a lot of things that I say already you know, but I want to take the history from the inception as we can identify that and then bring it to today and see what are the core ideas of AI, what they worked and when they did not work. So that the disclosure that we are supposed to do now, anytime that we use some large language models to get help for putting things together. So at the beginning, definitely was Alan Turing. And Alan Turing started with looking at what we call Turing machine. And a Turing machine basically is the concept of computation. So you cannot do anything in computer science specifically unless you have an abstraction. You need an abstraction such that you can bring the physical world in form of an abstraction, and then you can process it inside computers. But by his time, we didn't have computers. So the first abstraction was, what is a computer? And the Turing machine was the attempt to do that. You have an infinite tape, you have a tape head, a finite set of states, and a transition function to create a Turing machine. So that's basically a model of a Turing machine. But if it confuses you, just grab your cell phone. That's a Turing machine. Your computer, that's a Turing machine. So that's the advanced form. Same abstraction. Nothing has changed. We do not have a new abstraction for computational devices. So everything started in 1936 with what Turing gave us with his understanding. And then looking into the future before it even started, so Turing created the idea of the test. How do we know machines, if we create those type of machines that which meanwhile we have created, how do we know that those machines are smart? How do we know we can trust them? So he came up with this idea of testing them. So if you have two rooms separated, one is human, one is computer, one is AI, and then we have a judge who is a human expert, and then ask question, the judge does not know which room is which room. And then the job is to find out, if you ask the same question from the human and from the computer, and you don't know who is who, can you figure out which one is the computer? So how long does it take for the computer to say something stupid that we realize, oh, no human, we say that. So for ChatGPT, it took me 8 seconds. So when ChatGPT came out, I said, oh, okay. And my grandma, I'm pretty sure she still thinks ChatGPT is very smart. So the Turing test has to be done by an expert, not by a regular user. So that's why we make our life easier by assuming that things are smart when they are not. So what are the core concepts in our AI? Of course, we have to start from the natural neuron. So the natural neuron with all its anatomy and structures. You have the nucleus, you have axon, you have the dendrites, you have the bifurcations. When you learn some things, we use the myelin sheath to protect what we have learned, such that the neurotransmitter do not lose the information. And of course, the most important thing in a neuron, in a natural neuron with all its diversity, is the neurotransmitters, the synaptic connections. So the synapses, which we call in AI research, we call weights or parameters, more recently, are the ones that in natural neurons, they are quite complicated. We know some of the functionalities. There is a lot of stuff that we don't know. Neuroscience, biology, anatomy are working on it, and we learn more and more. But the connections between neurons to build a network is basically managed. The information is managed by synaptic connections that are either in excitatory state or inhibitory state. So, and of course, adult humans have around 86 billion neurons. We have actually much more. We have 200 billion when we are a kid. And when we grow up, we lose many of them because we don't need them. So we just become rigid and a little less learnable, which is very strange. But more than neurons, we have the synapses, 100 trillion to a quadrillion connections, which is actually the magic. if you look at zebrafish, you have 10 million to 100 million. And if you look at a bee, you have 850,000 to a million. But even if we have cases where we know basically every single neuron under a controlled laboratory environment, and we still don't know what is happening. So when people cannot even start looking at the concept of what is consciousness, how does consciousness emerge from those neurotransmitting activities? So a question that is probably too early for us. The artificial neuron is then the abstraction of the natural neuron. It's a tough job to do. So that was the beginning in 1943 by McCulloch and Pitts to come up with the idea of a mathematical model of neurons. So every time that we came up with an abstraction, for the first time, the abstraction of the natural phenomenon, something big happened. So that was definitely the beginning of artificial intelligence, that we came up with an abstraction and say, okay, natural neuron looks like this, a mathematical neuron should look like this. So it should have some inputs and outputs. It should fire, which means a signal should come in, and sometimes the signal goes out, sometimes the signal doesn't go out, and so on and so forth. So they call that threshold logic unit, TLU. So that means you have some inputs, and that's you have some weights, the synaptic connections. It goes into a function that just sums them up. And then it goes to a limiter. Why limiter? Because thousands and thousands of signal come in. Any biological or technical system has a capacity. You cannot just endlessly let things flow in. Then you need to limit things. So that limiter, which nowadays we call activation function, is the purpose is, okay, you cannot just endlessly put electrochemical signals on me, or simply electronic signals, and then you calculate the output. From today's perspective, that seems trivial, but that was not short of a revolution, that we came up with an abstraction of an artificial neuron. So that requires a lot of insight in both sides, that requires talented scientists to do that. So the artificial neuron, basically you have your inputs and outputs, and the weights or parameters, the synapses, are, based on everything we know, based on neuroscience, everything we know, are responsible for learning. So the changes in those synaptic connections or weights in the artificial neuron is what constitutes learning. And of course, you have a limiter, which is, we call a transfer function or activation function, is to, again, limit. So in computers, so in biology, so you can easily go over the limit, and in technical terms, so you get an overflow. You cannot endlessly add things up. If you add things up, you go beyond the biggest number that we can calculate. So you have to limit things. Simple things, simple limitations. So the artificial neuron was interesting because as the core idea of artificial intelligence, because fundamentally what it does, it creates a line. It draws a line. At any artificial neuron, the only thing that it can do, it can draw a line. And it doesn't matter how many inputs it has 2 inputs or 1 million inputs, it cannot draw more than a line. It's just a line. So you can simplify it and say y is equal a times x plus b. That's it. But we have w1 times x1 plus w2 times x is a line. If you go in multiple dimension, it's not a line, it's a plane. If you go higher, it's a hyperplane. But still, we are talking about the linear concept. And we do that because with an artificial neuron is actually, one artificial neuron is actually quite smart, and it can, let's say, separate a type of tumor type in lung. So lung adenocarcinoma versus a squamous cell carcinoma, tumor type. For a pathologist, for a physician, easy job. So it's a tumor type. It's not a big deal to say, this is this type, this is this type. But also with a single artificial neuron, theoretically, we can draw a line and separate these cases. Of course, in the reality that we see now, we have 2 red lines, 2 lung adenocarcinomas in the green area, which means you have some error. But depending on the number of features, those number of misclassifications will arise. So you cannot really do the job with 1 neuron. You need more neurons. And then we get started with the research. So this side is your line gives positive value. That side your line gives negative value. Very simple. Binary classification. You have a decision boundary. Starts with 1 artificial neuron. The most arguably the most valuable core idea in the history of computer science, I would claim, is the abstraction of natural neuron. Make it, okay, bring the abstraction into the computer such that we can work with it. But in order to separate those things, which is understanding it, you can separate oranges from apples if you understand this is apple, this is orange. It's not easy. You need a certain level of intelligence to do that. The more complicated those objects get, the more complicated the decision model. How many lines can you draw to separate them? Infinite number of them. So if you want to do randomly. So, but you need one, specifically one that perfectly separates them as far as perfection is possible. So, and that line, that blue line that you see here is given by specific values for the weights W1, W2, or to Wn. So you have to find those weights. You have to find the value of those weights. So how do we do that? If this is just a light bulb and I put 10 million neurons together, what is 10 million? Right now we have billion. So the large language models have gone over several billion parameters, which is you have several billion of these neurons. So, and now you want to adjust these values to make some sort of decision. How do you do that? So that's not going to work. There is no equation for it. There is no linear equation system that you can apply. There is no conventional mathematics for it. That's a tough job. So that's why most researchers have been doing in the past 60, 70 years old, past years. So the Hebbian learning started the research mainly from biological perspective, that again, the changing of synapses govern the learning. That's what we know. So that if the synapses change, we can learn something. So, and the basic principle for synaptic plasticity is that if you can, group of neurons can form together and then can change in strength and response to some sort of activity. You need some stimulus. So something changes, some response comes, and then group of neurons, circuits, subnetworks, there are different terminologies for that, gather together to do a specific task. So, and then when you do that, associations can be formed. So if you feel warm, there is a certain association. What does that mean? So I'm sleeping, I'm in bed, and I feel warm and cozy. So that's an association. So if I'm driving on the highway and a car passes me really fast, the association is I have to be careful because now I sense danger. To much more complicated association. So the relationship between the stimulus and to response becomes really strongly connected, and we learn that through changing synapses in specific subnetworks or circuits of the brain to learn those type of association. So the Hebbian rule, and this is, I'm not using many equations, but this is a historic one and the one that comes after that. The Hebbian rule basically says the amount that the delta Wij, so is the amount of change that you need to adjust the synaptic connection to learn something specific. If you want to learn smoking is bad, how much should I change? How many neurons should I change? Where should I change them? Very difficult. So, and then of course you have a parameter eta, which is just a learning parameter. It is a setting, it doesn't matter. And then you have xi and xj, which are activations of presynaptic and postsynaptic neurons. Very general rule that if you wanna, how much change the synaptic connection has to be undergoing is direct connection of what is happening before and after that neuron. That's basically what it says. Eta is, okay, you put eta to 0, you don't learn. You put eta to 1, you completely trust your sensations. Well, we don't want to completely trust the sensation. There have been 300 years of discussion going on in human perception. So can we trust what we see? Or I don't know how many books we wrote about how can I trust what I see? Now we say, yes, we can. But when you come to the conclusion, can you trust the conclusion as well? Then we came to delta rule, another core idea in the 50s and 60s that took the Hebbian rule, which is a biological one, and says, okay, now I need the abstraction. I have to bring it to the computer. Those presynaptic, postsynaptic doesn't cut it in computer science. I have to make it more concrete. How do I do that? Well, we made it more concrete. Say that the amount of change that I have to make to one weight, not even one neuron, one weight, So you see, when you do abstraction, you have to simplify things to the painful limit because you cannot otherwise establish things. If I want to change one weight and X is the input of the neuron, how should I make that adjustment? The adjustment is D minus Y. Y is the input, what you calculate, and D is the desired output. So the difference between desired output and the actual output, D minus Y, is the driving force, the error. That's a gigantic abstraction. That's a fantastic core idea. Trivial from today's perspective. Every bachelor student should know this, not even master or PhD student or professor. But from the 50s and 60s perspective, to take that step, to come from the Hebbian rule to the specific explicit delta rule, that was a gigantic step. And we said, okay, if I want to change this weight, I have to know how much it contributes to an error. How do I know the error? I know the desired output. Do we know the desired output as the human being? Well, desired output is whatever gives me a cozy feeling. I'm not hungry. I'm safe. I have food. Nobody's trying to kill me. That's the desired output. Very vague, very general. But everything we do toward that to get that desired output. In computer science, we have an easy life. We have an Excel file, a CSV file. We have the inputs. We have the output. Okay, that's the desired output. Calculate that. So we get to 58. Now, Frank Rosenblatt comes in and provides a schematic representation of connection in a simple perceptron. Okay, what happens now if I put some of those neurons together and I want to teach it something? So the first type of neural network. Now, this is a next level of abstraction. So if I take it and I want to make it functional, what does it take? To make it a perceptron, to perceive something, to have an automaton. The word has died. Nobody uses the word automaton anymore because that comes from symbolic oriented AI. So, and then make it to do something specific. It was such a revolutionary idea that New York Times around that time wrote that the embryo of an electronic computer, so the perceptron is the embryo of an electronic computer, expect that you'll be able to walk, talk, see, write. Oh my God, talk about exaggeration. Just because of an abstract idea by Frank Rosenblatt. They thought now we can create machine that can walk, talk, see, and so on. We cannot even do that in 2024. We can do some of it in a very controlled environment with a lot of assumption, with a lot of mistakes. Yes, but that was 1958. Such a great expectation. No wonder we got the first AI winter sometime after that. So, but you cannot do that unless you have a way of learning. How do you learn? If every neuron is a light bulb and you put 1 billion of them together, and each one of them has input output, how do you adjust billions of weights? How do you do that? So 1959 came the idea that let's use something that later called gradient descent, another core idea in artificial intelligence. So minimizing the error. Okay, we knew that. People told us, McCullough and Pitts told us, and Widrow told that about the delta rule, that we should minimize the error. So you have to make a small adjustment. From day one, we knew that we cannot make big adjustments. That's one of the striking wisdoms of scientific research in AI. From day one, we didn't know how to do it exactly, but we knew we have to do small adjustments. Because if you have 1 billion parameters and you want to make big adjustment, you will oscillate. You will go from good to bad, bad to good, good to bad. There will be no equilibrium. So if you want to get somewhere, you have to make small adjustments. You have to go slow. You cannot do that if you want to go make big changes. Yeah, you have to do it in iteration, of course. It takes time to decrease the error and then learn something. And then you have to automatically learn and improve. All of them from today's perspective, trivial, big deal. Of course, you're doing this. Yeah, that's machine learning 101. Yeah, I know, but this is 1959. It's not 2024. So, and gradient descent is interesting because the core idea of the gradient descent, because it looks at the diagram that we don't see. You do not see this curve. This curve is hyperdimensional. We usually don't see it. We see a very simple copy of it, but we don't see this in action. But what we imagine with learning should look like this. The abstraction is this. You start somewhere, and you're training. What do you do at the beginning? All weights of your fantastic neural networks with a billion parameter get random values. You start, if this is Milky Way galaxy, you start somewhere in the Milky Way galaxy, and you have to get somewhere specific, to a specific address. You take some steps, learning steps, you start decreasing the error. Oh, if you can move in the right direction, how do you know in which direction you should go? Big question. Gradient descent should provide some answer. And then you converge to a solution when you get to the minimum error. Can you see the minimum error? Are there other low values that may deceive you that they are minimum? Yes, of course. You can get stuck in local minima all the time. We didn't know that back then. So, and then, so if you can put this together and you can do this, then you can now put things together and make it a multi-layer perceptron. Neurons, perceptrons, now I can make a multi-layer perceptron. Now is 60s and 70s. And we can say, okay, I need an output, and then I can put several layers together of neurons and say, why layers? Because this is the simplest thing we can do. To this day, we are keeping this. And that's one of the problems that maybe at the end, so I will come back to it. We are going feed forward. We still are doing feed forward. We will be doing feed forward for the foreseeable future. That's a major restriction we have in artificial neural networks. There is no solution at the moment for it. Well, no practical solution. So you have an output layer, you have a hidden layer, you have an input layer. So now you have layers, so you have multi-layer perceptron. When we say perceptron, it could be an individual neuron, but it does something. It perceives. It's an automatic machine that learns something. It can do something. So data comes, feed forward, goes through it. You make a decision. You take some input and you do something. You say something. You make some decision of some sort. So the backpropagation was the first approach, or the first idea, the first next abstraction to implement gradient descent. How can I move across the minimum error, get to the minimum error, and then at the moment, minimum error for everybody. So to satisfy all neurons that I have, all millions and billions neurons that I have. Paul Werbers came up with the idea in 1974, and as it is in the history of science most of the time, so it's not necessarily the first guy who come up with the idea that will solve the problem. He or she will just struggle with the first challenges, say something, establish something, is imperfect, is not working, he gets forgotten. And then maybe some years, some smart PhD student will pick it up on the other corner of the planet and say, this is actually a fantastic idea. Let's work on it. Why? We come back to this. When Rumelhart picked it up with Jeff Hinton, the gentleman that Ernia was mentioning with Nobel Prize, and we looked at it again. So the backpropagation that was in 1974 was not a practical backpropagation. The main idea was take the error that you have at the output, put it back into the network. How? Well, I don't know how, but you have to do this. Okay, so it was not explicit. When the ideas are not explicit, then they don't get anywhere. So the backpropagation is basically backward propagation of errors based on a loss function. You can call it error function, energy function, anything else you want, with respect to all the weights. That's the core idea, all the weights, the error with respect to all the weights. You cannot leave some weights behind. We will see that when we get to the problem of vanishing gradients, that can be a gigantic problem. You cannot learn with half of your brains. And these are crucial ideas. They sound and seem trivial, but they are not. They are absolutely paramount to do things in a specific way. Then you update the roots. So minimizing the loss function, the error, to update all the weights. So his work did not receive immediate recognition, Paul Werbers, but it was rediscovered, and we will come back to it. So to talk about it, how it was. Without backpropagation, to this day, nothing would work without backpropagation. We do not have yet, still, 1974 to 2024, we still don't have any other way of doing it, of learning it. That's interesting. That's amazing. That's amazing. We need some of those smart PhD students to come up with the new methods. We do not have an alternative for backpropagation. We are talking about feed-forward, backward. We have some ideas, very theoretical, no practical results yet. Then we got to the Boltzmann machine. Boltzmann machine is very, very ambitious core idea in artificial intelligence, because Boltzmann machines, the connected graph, actually resembles how the human brain is. In the 3 dimensions, you have billions of light bulbs, and they are all connected in the space. Is not layer in 2-dimensional, layer of layer. No. In the space. That's how the human brain is, in the space, in the 3-dimensional space. But if you have that, if you have a fully connected graph, which goes back to works of enlightenment, starting with Euler and calculus by Newton and Leibniz and all that loss functions, AI without those guys would not have been possible. It's very interesting that now the reverberation of enlightenment is still reaching us. It's like the echo of Big Bang, that we can still 2% of the noise that we can hear is coming from Big Bang. It's amazing. There would have been no AI without the work of enlightenment scientists. No AI. So, and connected graphs goes back to Euler. So we without that fundamental work, we wouldn't be here. But when we talk about a graph like this, we only talk about visible and hidden neurons, because in a layer network, we know this is the input, this is the output. But if you have a connected graph in 3-dimensional space, things get very complicated. And how should I learn here? So Boltzmann machines are stochastic machines, basically, that follow probability distributions. And everything that we do right now, so the underlying things, we have linear algebra, we have probability theory, and every artificial intelligence neural network that we have is an automatic manifestation of either linear algebra or probability theory. We have not invented a new discipline in mathematics. It's all that, but we are figuring out how to do it in an automated way, in a meta-heuristic way. So, and Boltzmann machines are energy-based, energy functions. So we look at the likelihood of the observed data. So how likely is it that this belongs to this class? And of course, limited capability, because MLP is still widely used, but how should I train a 3-dimensional graph? I don't know where is the beginning, where is the end. The multi-layer perceptron is easy. Come here, go there, and I can go back here. I can follow things. The trajectories are clear. Nothing is stochastic. We are scared of being random. Randomness is, the god of randomness is merciless. You cannot really deal with that. So we need some level of deterministic behavior if we want to be able to use this. But the MLP had a big problem. And we needed some core ideas to get over the limit of multi-layer perceptron in the 80s and 90s. So the problem was, if you have complicated data, like say tissue images, a biopsy case, we would design manually some features that describe that complicated data. Is it molecular data? Is it imaging data? Is it any type of lab data, blood, whatever you have in medicine? So you would manually design something that grabs some features that you would think are important. You would start, okay, what is the average? What is the standard deviation? What is the color? Give me the color histogram. Give me the skewness of the histogram. Things like that. And then you would feed those features into an MLP. And then you would expect that MLP tells you, okay, this is breast tissue, this is lung tissue, this is adenocarcinoma, this is whatever classes you were interested in. And we were using it mostly for classification. So, and of course, this was not working. The information in the data, you are manually trying to get the essence of the data. And then any network cannot be better than the feature that you extract. That was a major problem. We needed some core idea to take the control away from the user for feature extraction. Don't touch the data. Give me the raw data. You mess it up. You bring your bias. With your limited knowledge, you don't understand the data anyway. You have 10,000 parameters. How do you want to know what features are important? You don't know. We don't know. Look at the papers published in the 80s and 90s. A lot of papers. You could do a PhD with just writing an edge detector for images, a 3x3 matrix. I designed it like this: -1, -2, -1. There you go. You have a PhD thesis. Problems were difficult. It's not, from today's perspective, very easy. So feature extraction was we needed some core idea to go after that. The core idea came in 1980, neocognitron. And the core idea was this: take the feature extraction away from manual design. Give it to the network. The network should decide what features are important in the data based on what you want from the data. Because this feature may be important for classification, that feature may be important for prediction. We don't know. So neocognitron was a fantastic idea, was the predecessor of convolutional neural network. And we had the feature extractions, S cells, and pooling C cells. Okay, the data comes, you extract features, you do pooling, and then you make your decision. Why do you need pooling? It's like limiter. When you extract features, there's a lot. We cannot handle it. Not as human, not as a machine. We always need compression. We always need reduction because it's too much. We are limited biological and technological entities. We cannot deal with that level of data. We always need to limit it. Compression, encoding, pooling, which is another fancy word for making it small. Just make it small. It's too much. So, but neocognitron was based on the idea of local receptive fields, hierarchical feature extraction, spatial invariance, and it paved the way for CNN. However, it failed. It was a core idea. It opened the door. People realized, oh yeah, we should look at it. The network should get the features themselves. When you look at the pictures that builds on the retina, and then the signals on the rods and cones go to the optic nerves, and then through the optic radiation goes to the visual cortex in the back of our head. Nobody filters that. Nobody does anything. The signal goes there, and something happens along the way that we encode the visual information in some way because there's a lot of information. If I just look at you in high resolution, so it's a lot of information. How do you do that? We didn't have effective learning algorithms yet in the 1980s. The computational complexity was huge. We didn't have training data. We needed to manually configure this. You cannot do that. And we did not fully understand the theoretical implications of this to do it. So 1982, the core idea of self-organizing maps was born. That if I look, maybe I bring the idea of collaboration and competition. And if I arrange, that's a core idea. If I arrange the neurons not as layers, but as a map, if I do that, then for every class, for every category, for every concept, I try to localize a winning neuron, a neuron that represents that problem, that class. So that's the winning neuron. But in the neighborhood of it, also the knowledge will be shared. So, and that neighborhood will be crucial for understanding the vague boundaries of the data. 1986, probably the most decisive core idea of AI was born, which was going back to Paul Verbus and rediscovering backpropagation, but this time going in detail and said, let's make it work. Let's make it work. So if inputs come, you have a layer of data, and then you have another layer, everything is fully connected, and you bring it to the final neuron, and you make a decision. The question is, how do you make that? So, okay, you take the error, which is the calculated output minus the desired output, and then you put the error back into the network one by one. And there was some mathematics put forward in 1986 in contrast to what was done in 1974, that we should do it this way. But not everything was still clear how exactly we should do it. So if I have an artificial neurons and I have my inputs and I have some weights and I sum them up and then put them through some limiter and I get an output, and I'm not happy with the output because the output is different from what I want to see. So, because I have data, which we ignore all the time this question. The data is human knowledge. We are trying to learn human knowledge, which we are assuming the human knowledge is reliable, is free from bias. And people now talk about AI being biased. Of course AI is biased because we are using human society. We are racist, AI will be racist. Very simple. You want to solve the AI bias, go solve the human society bias, which is a bigger problem, much bigger problem. Let's deal with that. So if I have the difference between the actual output and the desired output, then I have to put it back and calculate proper amount of adjustment to the weights of one single neuron, delta 1, delta 2, delta 3. But that's a difficult task because how much should I change? How should I decide how much should I change? So the backpropagation, or simply backprop, is for training neural networks, minimizing the error between predicted output, actual output, by the gradient, the change of the loss function. How much am I losing the error to get the minimum error? So the problem, which is we are still dealing with, in computer science, we are still dealing with this for different type of problems, not necessarily artificial neural networks, credit assignment problem. One of the toughest problems in computer science. So 1986, again, backpropagation. If I have a network and I get an error, so I send the entire data through it, and I get the total error of 125.65, whatever that means. The error doesn't have a unit. What is the perfect error? 0. 0. I want you to learn whatever I teach you. 0. So a big number is a bad news, is a lot of error. I want the error to go towards 0. So I take that error. Well, I want to make changes to the weights, to the synaptic questions, but who is responsible for that error? Now I'm training ChatGPT. I have more than 1 billion. I have more than 1 billion parameters that I have to adjust. Who is responsible for that? So who gets the credit for the error or the punishment for the error? So the output of a network is the result of many interacting neurons and connections. Things are superpositioning. You cannot separate them easily. There's a lot of overlap. That's actually the reason that AI can generalize in many cases, because we have overlap. One single neuron inputs contributes to many, many different decisions at the same time with different strengths. That's the actual strength. So the weight adjustment, that's a core idea. That's an app that this is probably the second and last time that I show equations here. That's a core idea. The weight adjustment delta W is minus, which is opposite direction of error. Opposite direction of error growing, I have to go in other direction because I want to minimize the error. Eta is a learning rate. 0, I'm not learning. 1, I'm 100% learning, which is dangerous. So that means whatever comes, you trust. No, don't trust. So we may start with 0.5 in the middle. So it's just a manual setting. And then is the gradient, the actual gradient, the change in things, this core idea. I always tell my students, so if you don't understand this, don't write a PhD in computer science. I know this is basic, I know, but do you get this? Do you understand what does that mean? So you can simplify it by the chain rule. Again, now we are looking at how much error changes when the neuron output changes. Error as a function of output. And how much it changes, how much the neuron output changes when the weight changes. The chain rule, differentiation. Thank you very much, Sir Isaac Newton. Thank you very much, Enlightenment. Again, I'm not exaggerating that whatever we have right now is still reverberating from what we got established during the scientific revolution after the Enlightenment. So we have this, so we can have an answer for the credit assignment problem. We can say who is responsible for the error. You are less responsible, you are more responsible. If you are more responsible, I make big changes. You have the complete wrong weight, so I have to make a drastic change. So your delta will be 0.75. and you are not responsible, okay, your delta will be 0.02. So problem solved. Well, maybe. Well, we hoped so. So the backpropagation was, before backpropagation, it was a dead end, and backpropagation brought a lot of enthusiasm in the late 80s and beginning of 90s when I got started in artificial neural networks. So, but we had a persistent challenge that, again, we needed some core ideas to solve it. Before 80s, before 90s, if you had 3 layers, you could easily train them, but you could not do anything exciting with it. You could not do face recognition, signature recognition. You could not recognize cancer. You could not do anything with 3 layers, but you could easily train them. You realize you can do really interesting things if you have more than 5 layers, but you go 5 layers, you cannot train them. What do you mean you cannot train them? They would not converge. The training would go on and on and on and on. It doesn't stop. You would not get to the minimum error to stop. And if you prematurely stop, the output was just messy and chaotic. It was not a deterministic reason. So that was a challenge. We got a second AI winter because of that, because everybody said, we are spending so much money and AI cannot even recognize signature. Who cares? Let's get some edge detector and then some other algorithm. Who cares? AI is not working. It's a dead end. You could not get research money in the late 90s and beginning of even 2000 if you were an AI researcher. Okay, you should do again symbolic AI, maybe fuzzy logic, because Japanese were doing that, but not artificial neural network. That was a dead end, in spite of the backpropagation, in spite of the multi-layer perceptron, because we could not, even with backpropagation, we could not go, so many core ideas, we still could not build a large network. And you can become intelligent if you have many neurons. Well, we are smarter than zebrafish, I would claim. Is a huge philosophical claim that we are smarter than the fish. I don't know we are, but we have more knowledge, let's say. We have more knowledge than the fish because we have bigger brain. So Backprop was the base for the deep network. So in 2000 and 2010, the Backprop became the central to training artificial neural networks. I don't want to say too much about the recurrent neural networks. You need sometimes the memory of what was before. And unlike feedforward networks, you need some directed cycles to learn what was before. And in recurrent neural networks, basically, you have a connection from neuron to itself. I don't want to spend too much time on it for different reasons, among others, because recurrent neural networks have not been as successful at feedforward neural network. Doesn't mean that we will drop them. No. I don't say anything about LSTM, another core idea, which is the predecessor of transformers, just because we don't have time. But if you have connections from neuron to itself, it creates problems for learning. So if you're telling yourself something, you need backpropagation through time, and you get vanishing and exploding gradients. So it causes theoretical and practical problems if you have recurrent networks. Well, you need recurrent networks. You need connection to yourself. You need to say something to yourself. What was before? Go back to the core of the computer science, Markov decision process. How many steps should I keep to know what is the next come? If I have Markov decision process order 1, so if I know what was before, I can say anything. So can you analyze my behavior just based on the last hour that I had some food and some coffee? Or you need to know how was my childhood? It's very different. So that's the difference of sequence processing. So how many steps do I need to go back? Recurrent neural networks lay the foundation for that, but we don't go much to it. So I want to get to 1989, the beginning of everything. And we came up with convolutional neural network, the improvement of neocognitron. So now we have something practical that says, you know what? Take an input, apply convolution, which is filtering, apply max pooling, repeat that, convolution pooling, convolution pooling, convolution pooling, and then you can use your fully connected multi-layer perceptron to make decisions. So again, convolution, which is another word for filtering, which is extract what is important. That's what it means. Extract what is important. How do you know what is important? You tell me what you want. I will extract to generate your desired output. Whatever is salient for your output. So this, and 89 was not the boom, but it was the theoretical breakthrough. So we brought three secrets, three core concepts. Learning to filter. Before that, again, we had manually designed filter. Signal processing engineering, big part of it was filter design. You would sit down and just on the paper design filters. That didn't go anywhere in artificial intelligence domain. Weight sharing, sorry for the typo. Weight sharing, core concept, and divide and conquer. So three core concepts that helped us. So, okay. Hopefully you can hear me now. Sorry about that. Okay, let's continue. So we talk about filtering so that you have an image and you apply filter. And those filters in the middle, they were usually back in the 80s and 90s and even into 2000 were manually designed. Again, you would sit down and based on signal theoretical considerations, you would design them. But now if I take it out and I have a set of filter for the entire image, your image could be 1000 by 1000 pixels and your mask is 3 by 3, 5 by 5. So if you learn that filter, you apply it on the entire image, that's weight sharing. So you learn one filter of 3 by 3, 9 values, 9 synaptic weights, and then you apply it on a million pixel, 1000 by 1000 image. Weight sharing, very powerful idea. Not only you are learning the feature yourself, but also you are doing it in a very efficient, fast manner. And we finally figured out how to apply the core idea of divide and conquer on artificial neural network. It's not an easy thing. One of the major strengths of any computer scientist is, if I give you any problem, can you tell me how you would apply divide and conquer? Not easy. There is no general recipe for that. You may spend years of research on it and say, oh, okay, we should do it this way. It took us more than 20 years to do it for neurocognitron. So you take the image, you apply filtering, so convolution and pooling, convolution pooling, convolution pooling, convolution pooling. Why you do it excessively? Because you want a hierarchy of filters. You want features at different levels, at different scales. Because if I look at the forest from distance, or I looked at the bark of a tree close by, I see different things. So we want to see all that. So we need filtering at different scales, and then we need to compress it at different scales. And when we get to the bottom of it, then I can just classify it, which means I do feature extraction with repetitive use of filtering and pooling, and then I use an MLP, the good old-fashioned MLP. To this day, we are still using MLP for the final decision-making, which means this is the divide, this is the conquer. It took us 25 years to figure that out. And it took us additional 10 years to make it practical. So you figure things out theoretically, but it is not necessarily to make it to the practice. It still needs some time. So, and then pulling, of course, the internal divide. So then you pull, so if you look at the blue one, 3, 4, 2, 3. So the maximum is 4. Look at the green one, 6, 5, 6, 7. Max pulling give you 7. Why maximum? Well, artificial neural networks, natural neurons, fire together, wire together. So if you have a signal, the maximum signal is the maximum activity. So it has some biological equivalence. That's why we use max pooling as something meaningful. So, and you, of course, reduce from 16 values to 4 values. 2006, restricted Boltzmann machine, absolute core idea. That's the beginning of actual revolution. Still, CNNs cannot be applied. We have the CNNs, but we cannot apply them. We cannot use them. So restricted Boltzmann machine is a crazy idea. It's one of those crazy ideas that you, if you have spent some time knowing support vector machines, and when you understand what does it mean, what is the kernel trick, how do you go from one dimension to dimension, and you cannot solve the problem in this dimension, and you bring it to the higher dimension, which is more complicated, now you can solve the problem. It's a crazy idea. Restricted Boltzmann machine is at the same level Crazy. So if you look at the Boltzmann machine, which is a stochastic probability distribution machine, which we cannot use, is a much more realistic implementation of human brain, abstraction of human brain, but we cannot do it. There is no way for us to apply backpropagation on a three-dimensional light bulbs. That's not gonna work. We would love to do that, but how? So if we design hidden nodes and visible nodes, and we remove the internal connection between the hidden nodes, and we remove the connection between the visible nodes, and we get the visible nodes out, and we get the hidden nodes out, and the remaining connection stays, that's a multi-layer perceptron. No, 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 no. That's a restricted Boltzmann machine. Why? Because Boltzmann machine was good to learn probability distribution. I just put some condition on them. I still can do everything with them. Like what? Like learning probability distribution. Is that new? Yes. In artificial neural network, it's true. It's true. And it's new. It's interesting that if you are not deep in the subject matter, we have difficulty to understand the innovation. And that's the struggle of the guy who innovates. Because he has to make the rest of us understand this is new. Yeah, it looks like multi-layer perceptron, but it is not, because you can learn probability distribution. So when you go to visible to the hidden one in this two, basically the hidden one should be smaller than the visible one, but it should learn the same probability distribution. What is the task? No task. No task. You learn the distribution. Fundamental shift in artificial neural networks. So what I think, Jeff Hinton has done a lot of contribution, but I think this one deserved the Nobel Prize. Because this made it possible for us now to train deep networks. Without restricted Boltzmann machine, we would not have been able to train any deep network, including ChatGPT, any deep network. So restricted Boltzmann machines were used to pre-train deep networks in unsupervised manner. Keyword, unsupervised. You don't need output to train networks if you use RBMs. And he came up also with contrastive divergence algorithm to train them in an unsupervised manner. Connected to now autoencoder, another innovation from the group, from Jeff Hinton, and developed in the 80s and 90s. The idea of autoencoder, again, sounds one of those things that say, for heaven's sake, what do you want to do something like this? So if you look at the concept of autoencoder, it's there to compress representation, to compress vectors. We use fancy words, vectors. You want to compress vectors, any vector that has semantic meaning, not just random numbers. It has semantic meaning. And you want to use backpropagation, you can do dimensionality reduction and feature learning. So you have a vector that is something, whatever it is. You want to compress it, compress it, compress it, compress it. And then you want to build it back up and create the same vector. So X goes in, X comes out. Why you are wasting my time and computational power? What is the benefit of that? Well, the benefit of that is the bottleneck, the representation, the smallest compression that you have. So if you have 10,000 gene expressions, and then you put it 5,000, 2,500, 1,200, 600, 300, now you have 10,000 into 600? Wow. Now we can compute. Oh, okay, now you got me. So it's about representation. But like multi-layer perceptors, we could not still train this. We needed additional key ideas. RBMs came here. So how do we train them? This too is an RBM, is a restricted Boltzmann machine. This too is an RBM. This too is an RBM. This too is an RBM. What just happened? We just figured out a way to perfectly, in an unsupervised way, train a deep network. Wow. To this day, we don't have any other. Doesn't matter what network you use. Is it a CNN? Is it a transformer? It doesn't matter. You have to do this, otherwise you cannot start training. So that's the core idea that really changed everything. And when you do this, when you go through this multiple iteration, and you look at adjacent layers as being an RBM, they have to just learn. What does that do? It syncs them in the hyperdimensional space to speak with the same language. Okay, but what language is it? We don't care. They just speak the same language. Now I start learning in a supervised manner. They are synced. It runs smooth, like a Swiss clock. Amazing idea. And after you learn that, you just mirror the waves to the other side. Another key concept. So you learn the half of it, just mirror, do a transposition, bring the weight here. Now you have a perfectly ready to learn neural network. Doesn't matter how many layers you have. 500 layers, who cares? We can do it because they are synced. Fantastic idea. You can sit days on it and think about it. It's like this hopeless poets that sit down and look at the tree and say, oh my God, this is so beautiful. And nobody else sees that beauty. So RBMs is definitely one of them in connection to autoencoders. Of course, you get variational autoencoders, the beginning of generative AI. Not possible without RBMs. You cannot train a variational autoencoder as the beginning of generative AI without pre-training them in an unsupervised manner. The success, finally the success comes. Finally, that's 2012. Finally, the AI community has something to learn. The AlexNet beats everybody else, beats all other models and algorithms for the ImageNet. 1,000 classes, 1,000 objects from cats and dogs and airplanes and pedestrian, brings the highest accuracy of object recognition. Computer vision, one of the toughest things that we can imitate human intelligence. Finally, in 2012, we can do it. So because of all that, neocognitron, CNN, autoencoder, restricted Boltzmann machine, abstraction, backpropagation, all that flows together, and you train a CNN to recognize cats and dogs. So generative adversarial AI, GANs, of course, we don't want to just classify data, we want to generate data. So if the classification is you just learn to, where should I draw the line that say this is apple, this is orange, this is cancer, this is not cancer. But the generation works in a different way. And again, we go back to RBMs. Without RBMs, we wouldn't be here because RBMs brought us back from the cloud of artificial network to the solid ground of probability distributions. Probability theory is the strongest theory we have. It brought us to the moon. Nothing else brought us to the moon. Kalman filter brought us to the moon. If that wasn't a hoax, according to some people, but I think we went to the moon. So we had the technology to go to the moon. So you learn the distribution and you generate more data. What is it good for? When that was introduced, people said, what is this good for? I have my data. You want to give me more? What is it good for? Now we understand. And when you ask ChatGPT, write me a poem about somebody who is in prison and is lonely. Okay. It's not the best use of ChatGPT, but okay, now you understand what generation means. I asked ChatGPT, give me another tissue image that is an intersection between papillary and adenosis. No other technology can do that. What is it good for? Research, education, fundamental research. So GANs are interesting because, again, you get images and you have a real tissue, and then you have some random noise. It's amazing. From random noise, you want to generate tissue, generate new tissue. From random noise, how can you make noise to tissue, to make an image, to something that makes sense? And then you give it to discriminator. The discriminator has to say, this is fake, this is real. Core idea, the generative adversarial network, core idea to double check. In going back to maybe the idea of self-organizing maps, that we combine collaboration with competition, another manifestation of sort of opposite learning. So you bring in the opposite. So this is real, this is fake. Can you figure it out? If you can figure it out, because at the beginning is easy. Noise is noise. Everybody says noise, 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 noise. You get to a point that you cannot say this is real or fake. There's that website I'm sure most of you have seen, that there are fake faces, people who do not exist, but the photos are there. The workhorse of artificial intelligence, the final core idea that we have had so far, we went beyond autoencoder, beyond variational autoencoder, beyond convolutional neural networks. We came to something bigger. At least according to Google guys, we came to transformers. That's the first time that a core idea, if I'm not mistaken, a major first time a core idea is not coming from academia directly. It's coming from corporations. That's a new era in scientific research. It has implications, and we see the implications. Now, major language models, major AI models, foundation models are, most of them, if not all of them, the reliable ones are coming from industry. That's good, and that's a point of concern. Because in scientific research, we are driven by other factors. Yes, academic ego as well, but overall picture for the benefit of the human society. Most of academicians are paid by taxpayer money. We are not supposed to work for profit. We get salary and we work. Yeah, we are driven again by our own ambition. But companies, I'm very thankful that we have good companies and they are doing all this. Fantastic. But is a new trend that now core ideas are not coming from academia anymore. That's a problem. At the moment, I see it as a problem. Maybe it's a blessing. I don't know. So, and you have seen this picture in the seminal paper of 2017. Attention is all you need. And that was a revolution in 2017. So the problem that was, we had two problems, long range dependency. If I have a document, so if you read a novel from Agatha Christie and you read through 200 pages and the final sentence says, and they found out Jim was the killer. So you have to go back and what was the dependency? What happened? If you want to write novels like Agatha Christie, let's say, if you have that ambition, I don't think ChatGPT can help you. You need a talent for that. But so what is the dependency? When the things come at the very last part, how do I find the dependency to trace it back and say, in order to get to that surprising effect, I have to arrange things in this way? Think about the correlation of complicated multidimensional data that we are dealing with. But the vanishing problem was the bigger problem. When you look at the long-term dependencies, a large sequence of data, text documents, molecular data, omics, gigantic images. So how do you look at that? So if you do that, you have really deep network. If you do that, you get the problem of vanishing gradient. So what does that mean? You go one epoch, you send your entire data to the network, you get your error. You calculate the error and say, okay, the error is 156. The first three guys, your contribution is 66, I connect you. Remains 90. Next layer, 55, I correct you guys. What is remaining is 35. Next layer, I have to correct 42, but I have only 35. When I make that correction, next layer, I have nothing to correct, nothing to correct. What does that mean? That means the layers close to the input will stay untouched. They are frozen. You are not learning with them. So, of course, you have very deep, if you from your 200 layers, 198, let's say, learn, and only 2 layers learn. Is that a big deal? It will come back and bite us at some point. Lack of generalization, hallucination, memory distortion, completely crazy responses, and definitely giving you some points for adversarial attacks because you know this part is weak. I can attack it here. Cybersecurity of the next 2-3 decades. So vanishing gradient is a problem. We needed the core concept, the core idea to remove this, to take care. That was the reason, among others, that LSTMs, long short-term memory networks, recurrent neural networks, they were not working because you made them deep to be able to handle large sequences. If I put a novel of 2 volumes of 700 pages, do you understand that? Wow, that's a lot. Well, give me RNA sequencing, that's even more difficult. How can we do this? So it was difficult because the sequential processing was difficult for parallel processing. Scaling was not possible. We could not grasp the context of the issue. The context is important. Are you getting surprised and impressed when you talk to ChatGPT and then you follow, and then he still understands you are saying, gets the context? How do we do that? How do they do that? Attention. So the core idea, the last core idea that I want to talk about is the attention. So if I look at a sentence that says, I would like to understand the AI applications in pathology, the attention most likely should be on understand, AI, and pathology. What are the key words here? That if I get those words, I got it. So attention, here is where some colleagues disagree with me, is a misnomer that we are using. This is not attention. The way that it is done in the transformer is not attention, it's correlation. But okay, if you are delivering really good results, you can do misnomer. Naive Bayes is one of them, fuzzy logic is one of them. So if you're successful solving problem, oh, okay, you get the privilege to have some misnomer, nobody cares. It's working, But it's a misnomer. From research perspective, can cause some issue. So we have different type of attention, scale dot product attention and multi-head attention, which is, we need to figure out, now the idea was we need to figure out to say what is important in a scalable way that we can go really deep. What is it? And here something happened that is fantastic, but is causing a problem that again will come back and bite us. And that's at some point we have to drop transformers. And I'm sure many colleagues will disagree with me. At some point, we have to drop them because they deviated from a major principle that we maintained back in the 70s and 80s. So what we call attention, and started in 2017, you get a query, you get some keys. So the keys represent the potential information offered by each word in the sentence. We are, of course, starting with natural language processing. That was the beginning of transformers. Understand language, not images to begin with. And then values. Values contain the actual content associated with each word. What is the value of each word? Which is the attention. What is the attention? And then you need some normalization factor and so on and so on. So attention calculation involves matching the query with keys. Now we are talking information retrieval language. But isn't that artificial neural network? Why we are talking retrieval language? That's the language of 70s and 80s. Keys, query, value. That's hash tables. That's data structures 101 in computer science. Why we are bringing this into artificial neural networks? But we want to selectively pull information from the values. So we are creating a lookup table, but it's not a deterministic lookup table. It's not a hard lookup table. It's a soft quasi-stochastic lookup table. But the stochasticity should give you diversity, not wrong answer. How do we do that? Just that one equation? No, with some topology. So input comes, we encode it, we get some features, we decode it, we get some output. Okay, this is new. Well, the way that we want to define it is new. Let's say I want to translate from German to English. I want to translate Ich bin ein Student to I'm a student. Text translation has been a major task for AI. So object recognition, text translation, summarization was a dream. Done. You can summarize any text. Not perfectly maybe, but we can. We can summarize text. Of course, you can multiply this. The input comes many encoders and many decoders when the problem is difficult. okay? So input comes, goes to an encoder, I get features, I put it into the decoder, n times each one of them, n times decoder, n times encoder. Why? Divide and conquer. The problem is difficult. Okay, principle has not changed. You're just finding another manifestation to do it in a different way. What we have in mind is understand long sequence. That's the motivation, which could also be the bias. That's the motivation. We want to understand. Recurrent networks did not work. LSTMs did not work. CNN cannot do this anyway. So we need something to process long sequences of data over time. How should we do this? That we do not have vanishing gradient. We can go really, we have to go deep. We have to go really deep. How do we go deep without getting vanishing gradient? Okay. Inputs comes in, encoding, 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 feature, decoding, 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 output. Okay. Good. I'm still with you. I don't know where you will lose me. Okay, maybe here you lose me. Okay, what's going on here? So I get the input. I come up with something new, positional encoding, because in the human language, we are focusing on language, position matters in the language. I am a student from Germany. You cannot say Germany, am I a student. It doesn't make sense. So positions matter. Language has structures. We have syntax, we have semantics. Okay, so we need some positional encoding. And then we encode. Positional encoding, so we can use sine and cosine. Sine and cosine? First time I saw this, I was surprised. Wait. We went away from conventional mathematics. Now we are coming back to trigonometry. So if I look at a document that I have that says, Ich bin ein Student, I want to translate this. So first thing is that I have to positionally encode this information. And I give to every token, which is, let's say, every word here, I give an index, 0, 1, 2, 3. I have 4 tokens. And I can create now positional encoding using some sine and cosine function. And then I get some values. So, and of course, sine and cosine, you get also positive and negative values. For example, if I look at student, and then I have P31, which is with bin, I am, is minus 0.99. What does that supposed to mean? Negative positional encoding. Well, in this context, could mean that bin comes before student. That's all it says. In a different context, it may mean something. Positional encoding, a key idea in transformers. Sometimes we suspend it because positions do not matter. In my case, in tissue images, position do not matter. In natural scenes, position matters. The sky is here, grass is here. Position matters. Sometimes it matters, sometimes it doesn't. So now, and the output size, the decoder part, when we send the output, goes through the decoder, and then a linear multi-layer perceptron, basically, a softmax, we get the output probability, we put the shifted output back into the system. What? Do you remember recurrent network? We said the neuron has connection to itself because you need the memory, Markov decision process. I need to know what happened before. So for that, we need to shift, bring back, shift, put it back as an input for autoregressive generation or sequence-to-sequence tasks, one token at a time. So then you have the complete picture. Transformers are very difficult to understand, very difficult to understand. So then you have the complete picture. That's one head. That's one head. I can have multiple heads. Then I can get context. A word can mean something in a poem, can mean something in a scientific article, can mean something in a colloquial conversation. For each one of them, you need a head. But that's fine, because then this structure, you can have parallel, you can send each one of them to one GPU. You can learn independently. Challenges of transformers, we are almost done. Computational complexity, they are data hungry, they are memory consumption, is becoming monopolized by everybody who has. Go try to see the CEO of NVIDIA. You will see prime ministers and presidents of countries waiting to talk to him because it has become a question of national interest to people to have GPU power. You cannot train transformers for reasonable tasks if you don't have the infrastructure. We cannot interpret them still. There are still black boxes. But the scalability and deployment, energy consumption is a big problem. Right now, nobody is caring about that because we want to generate results. Where are we? And we are done. We have a lot of success with generative AI, translation, summarization. ChatGPT is fundamentally a talking encyclopedia. I use it all the time, but I still double check and fact check everything with my physical Encyclopedia Britannica. So, but it will be perfected and it will be a talking encyclopedia. We can use it for many different purposes. Fantastic. But I'm not sure we are out of the Chinese room. I think still the room does not understand Chinese. The transformers have not opened the door that we go out, we understand language. I think we are doing exhaustive correlation analysis. The efficiencies that we have right now, with the transformer, we went away from the original AI ambition. That's a huge problem. We went back to manual design. You look at the structure of transformer, okay, our input comes here, and then I do this, and then I do the linear, and then I do normalization. That's a manual design. I thought we wanted to go away from that. CNN was much closer to the way that human brain works. Autoencoders are much closer to what human brain partly does. Transformers are not. What is the implication of that? You will not be able to imitate aspects of human intelligence with that. And they are still inaccurate in medicine, very inaccurate. I just give you, if you look at the left one, so the black one, that's the way that human brain should be modeled. Again, a Boltzmann machine. The middle one, if you have a subnetwork, the blue one that is working, doing something, it should be embedded within the gray one, which is the bigger brain. We don't have structures like that. And then look at that right one, what is the transformer? This is imitation of that? No. But it's doing fantastic things. Okay, I'm using it. But I'm not losing the picture that we want to go toward the graph one. The ones that Euler actually said, okay, this is what we can do with this type of structure. And they are very inaccurate. So recently, 4 or 5 months ago, and they are coming out, foundation models for histopathology, gold standard in cancer diagnosis. Foundation models were published. We tested that. We tested all of them. Accuracy less than 44%. But network, what technology? It has to be reliable. At the moment, we are not there. So thank you very much for your attention.